If there's one rule that people know about how fast things can move, it's that there's a cosmic speed limit, the speed of light in a vacuum. If you have any amount of mass at all, like anything made of atoms, you can't even reach that limit, you can only approach it. Meanwhile, if you have no mass and you're traveling through completely empty space, there's no other speed you're allowed to move at, you must move at the speed of light. And yet, if you think about how big the observable universe is, we know it's grown to 92 billion light-years in diameter in just 13.8 billion years. Moreover, by the time just 1 second elapsed since the Big Bang, the universe was already multiple light-years across. How is this possible without breaking the laws of physics? That's what Roberto Cánovas' son Lucas wants to know, inquiring, if the universe grew more than 300,000 kilometers in a fraction of a second, that means all these things had to travel faster than the speed of light during that tiny amount of time, thus breaking the rule that nothing can travel faster than light. If you want to understand what's going on, you're going to have to bend your brain a little bit, because both things are simultaneously true. The universe really does grow in this fashion, and yet nothing can travel faster than light. Let's unpack how this happens. Let's start with the rule you know, that nothing can travel faster than light. Although this rule is normally attributed to Einstein, it's a cornerstone of special relativity. It was actually known, or at least strongly suspected, to be true for more than a decade before him. If you have an object at rest, and you apply a force to it, it's going to accelerate. That's Newton's famous F equals ma, which says that force equals mass times acceleration. If you apply a force to any massive object, it's going to accelerate, which means it's going to speed up in a particular direction. But that can't be strictly true all the time. Imagine you accelerate something so that it gets faster by 1 kilometer per second with each second that goes by. If you start from rest, it would only take 299,793 seconds, about 3.5 days, before you reached and then exceeded the speed of light. Instead, there must be different rules at play when you get near that speed, and we figured out those rules back in the late 1800s, back when Einstein was still a child. People like George FitzGerald and Hendrik Lorentz, working in the 19th century, derived something spectacular, that when you got close to the speed of light, the universe you observed appeared to play by different rules. Normally, we're used to a ruler being a good way to measure distances, and clocks being a good way to measure time. If you were to take your ruler and measure a moving object, you'd expect to measure the same value as if the object were stationary, or if someone on board that object used their own ruler.